If one ugly 15-minute interval has ever added 5 or 6 figures to your power bill, this episode is for you. Today, we're decoding commercial and industrial peak shaving so you can see how to cut demand charges without creating chaos in your operation. I am Daniel Burke, and this is Energy Answers by Tactical Energy Group. I'm talking to you if you run a commercial building, an industrial facility, a manufacturing plant, a hospital, a university, or a data center, and you're spending far more time thinking about electricity than any normal human being would ever want to because the bill keeps going up and you're not exactly sure why. Here is the short version. Peak shaving is not about how many kilowatt hours you use over the month. It's about how high your kilowatts climb in the worst 15 or 30 minutes on the bill in the billing period. Demand is billed in kilowatts, and many tariffs set that demand line based on your single highest event. Demand charges can be 30 to 70% of a large commercial or industrial bill. Peak shaving is about lowering that maximum KW number during those key intervals, not necessarily changing your total kilowatt hour consumption. The decision in front of you is which mix of operational changes, on site generation, and storage gives you the best cost reduction for the least operational pain. So let's start with the foundation: KW, kilowatts, versus KWH, kilowatt hours. Energy consumption, the volume you use, is measured in kilowatt hours. That is the area under the curve. Demand is measured in kilowatts. That is the height of the curve at any given moment, typically averaged over 15 to 30 rolling minutes for billing purposes. You can keep your monthly kilowatt hours flat and still see very different bills if one month you have a smooth load profile and in another you allow a sharp peak to register. You see, utilities build infrastructure to meet the highest moments of usage, not the average. The classic analogy is the 12-passenger van analogy, where you buy a 12-passenger van, but you only ever haul around 2 or 3 passengers. You're paying for all of that 12 passengers of capacity, whether you use it or not. Demand charges are how that cost, the cost of maintaining the grid, gets pushed back onto large users in proportion to how much they contribute when the system is stressed. If your demand rate is $20 per kilowatt, every kilowatt you shave off your monthly peak is $20 per month, or $240 per year per kilowatt. At $30 per kW, that number gets even more serious, and on and up we go. Once you understand that, the rest of peak shaving comes down to 3 mechanical levers, and we're going to cover them all in detail right now. The first lever is load shedding and load shifting. This is about reducing or rescheduling non-essential loads during the hours when your demand tends to be highest. HVAC is usually the largest load in commercial buildings, for example. You can pre-cool or preheat before the anticipated high-cost window, then raise the cooling set point a couple of degrees for a few hours so compressors run less while you are in the expensive peak periods. Lighting is another example. Dimming or turning off lights in non-critical areas, warehouses, parking lots, or unoccupied spaces can pull down your KW without affecting the core operations of whatever business you're in. In industrial facilities, you can look at process optimization. Can large motor starts, batch processing, furnace operations, or other heavy users be scheduled outside of the utility's peak window? A steel mill might schedule its arc furnace runs away from the system-wide peak. Pumping systems at water treatment plants or industrial sites can be scheduled to fill storage tanks before the most expensive hours, then rely on that stored volume while you are in the demand window. EV charging is another area where you can delay or modulate charging so fleet vehicles do not pile on top of your worst intervals. The second lever is on-site generation. Diesel or natural gas generators and combined heat and power systems can run during the hours when you care most about reducing and mitigating that demand peak. Instead of drawing all your power from the grid during those windows, you run part of the facility off of your generator or CHP units. A data center might run its diesel units for 2 to 4 hours on hot summer afternoons to keep grid demand down while still maintaining full IT and cooling functions. CHP units that are already running can sometimes be ramped up during those hours as well. The third lever is battery energy storage. Here, you charge the battery during lower cost hours or from on site generation, then discharge during the peak interval. A 500 kW, 1 megawatt hour battery can cover roughly 500 kilowatts for 2 hours. Control system watches your meter in real time and starts discharging the battery whenever your demand approaches a predefined demand threshold. It's the same idea as setting a ceiling on your demand line and using storage to keep from punching through it. None of those levers work well without a control layer on top. Modern energy management systems continuously monitor your main meter and ideally sub-metered loads. They use historical data, weather, production schedules, and your tariff details to anticipate when peaks are likely to form. More importantly, they can act automatically, reducing the strain of behavioral change on your operators. When the system sees your demand climbing toward a threshold, it can shed selected loads, start a generator, or discharge the battery based on a set of rules you have already agreed to. You do not need perfect prediction for this to be useful. If your rule is never let demand go above 1.5 megawatts and the controls are set correctly, the battery will start discharging whenever your facility's demand climbs toward that established level. You're using controls to clip the top of the curve whenever it tries to reach the ceiling. Over time, machine learning based systems can look at past performance and refine when and how aggressively to respond. Now, we need to talk about sizing and math because this is where most peak shaving decisions are made or lost. You need at least 12 to 24, even 36 months of billing history to see your demand charge components and peak demand values. You want to know your highest recorded demand, when it happens, how often it happens, and for how long. Submetering is what shows which equipment is causing those peaks. A key metric is your demand charge cost. How many dollars are you paying per kW? Another is your historical peak demand in kilowatts. If you have a 1,000 kW peak and a $15 demand charge rate, consistently shaving 1,000 kW would save $15,000 a month or $180,000 per year. If your region is at $25 to $30 per kW, the numbers are even more amazing. Your load factor is also incredibly important. Load factor is simply the ratio of kilowatt hours consumed to potential kilowatt hours as determined by your peak demand in each billing period. A facility with a 500 kW average and a 2000 kW peak has a load factor of 0.25 in this scenario. That tells you your curve has tall peaks relative to the average and that peak shaving may have a strong payoff for you. Peak duration and frequency determine whether storage makes sense and how much energy capacity you might need. If your typical peaks last 2 hours and you want to shave 500 kW, you need around 1,000 kilowatt hours of battery capacity. If peaks last 4 hours and you need a megawatt of shaving, that's a very different battery or a strong case for a generator or combined heat and power support instead. Capital costs, of course, must be considered too. For batteries, you're often looking at somewhere in the $500 to $1,000 per kW range when you include equipment and integration. For generators, you might see around $300 to $600 per kW. A 1 megawatt 2 megawatt hour battery system can easily sit between $500,000 and over $1 million, depending on technology and integration complexity. So you need to consider these things. Most commercial and industrial projects are aiming for a payback in the 3 to 7 year range. That means the combination of demand charge savings, any demand response revenue, and any time of use or arbitrage benefits need to cover the capital and operating costs within that window and then keep producing after. So let's talk about how to match technology to your specific Use case. Battery energy storage fits best when your peaks are frequent and relatively short, typically in the 1 to 4 hour range, and when you also have opportunities to use the battery for demand response or time of use arbitrage. Batteries respond fast. They do not require fuel logistics, and they can participate in multiple value streams. If you go back and check out the episode we did on FERC Order 2222, you will understand exactly what I mean. You do have to factor in round trip efficiency. A typical loss of 10 to 20% means if you want to discharge 1 megawatt hour, you need to put in about 1.1 to 1.2 megawatt hours. Generators make more sense when your peaks are longer duration, 4 hours or more, or when you also need backup power for critical operations. Running a 1 megawatt diesel generator for 4 hours may use roughly 140 to 160 gallons of diesel, which at $3.50 to $4.50 per gallon is $500 to $700 in fuel plus maintenance. That is worth it when the avoided demand charge and potential demand response revenue beats those operating costs by a comfortable margin. CHP, combined heat and power, fits when you have a steady need for both electricity and thermal energy. In that case, combined heat and power can serve as a base load and ramp during peaks, offering high overall efficiency. Hybrid solar plus storage systems use solar during the day to charge the battery and then discharge during evening peaks, which can be very effective in time of use regions. Now, the risks and misconceptions around peak shaving. First, capital cost is real. A megawatt class battery or generator project is not a rounding error. For smaller facilities or tight balance sheets, that upfront cost can be the main roadblock. Second, operational complexity does go up. Generators need fuel management, regular testing, and compliance with emissions rules. Batteries require thermal management, correct cycling to protect lifetime, and eventual replacement. Load shedding strategies must be crafted so they do not degrade comfort, safety, or production. A rushed process shift in a plant can create bottlenecks or quality issues that cost far more than the demand savings they may produce. Third, aggressive load shedding can hurt if you push too far on HVAC or lighting. Allowing temperatures to drift too much in a hospital or dimming lights too far in offices or production areas can create safety or productivity problems. Fourth, permitting and interconnection are not trivial. Large generators, CHP units, and substantial battery systems trigger environmental reviews, fire safety requirements, and utility interconnection studies. All of that takes time and money. Fifth, stranded asset risk is real. Tariff structures change if you buy a long lived asset, such as a generator or a large battery, purely based on today's demand charge structure, and your utility later rebalances the tariff toward time of use rates or changes how demand charges are calculated. Your payback can stretch out quickly. Then there are the misconceptions. Peak shaving is not the same as reducing total energy consumption. In fact, it's not an efficiency measure really at all. You can install an excellent peak shaving system, keep the same kilowatt hours for the month, and still save a lot of money because you lowered the worst KW interval and you effectively controlled your demand charge. It's also not only for extremely large industrial facilities. With the drop in battery costs and better control systems, a 200 kW peak reduction at a medium-sized commercial building can still deliver a worthwhile return when demand charges are high enough. Generators are not the only tool anymore. For many applications, batteries are a better fit due to speed, lower maintenance, and ability to produce multiple services on top of peak shaving. You also do not need perfect prediction for peak shaving to be effective. A well-configured battery with a demand threshold can respond in real time as your demand climbs. And this is not a set and forget decision. Tariffs, operations, and equipment age. A strategy that works year one will need monitoring and tuning over the life of the asset. So, how do you decide what is most cost effective for your facility, if anything? You start with a comprehensive energy audit and load profile analysis. Pull 12 to 24 months of bills, identify every demand charge component. Look at when your peaks occur by time of day of the week, and season, and how long they last. Utilize metering and perhaps even sub-metering to see which loads are driving those peaks. Next, and perhaps most important, you have to read your tariff in detail. Read it properly. Identify all the different demand components and provisions. On peak, off peak, coincident peak with the system, non coincident peak. You need to understand in detail how the demand billing on your rate works. Understand whether your demand charges are based on your internal worst moments or tied to a specific system window, because that changes the strategy. Investigate demand response programs and other incentives and note what they pay per kW or per megawatt hour. Then look for low cost operational changes before you buy anything. Can you adjust thermostat set points a couple of degrees during certain hours? Can you dim or shut off lighting in non critical areas? Can you reschedule, especially heavy processes, to off peak times? This often involves getting production and operations leaders around the same table as the energy team, and that is such a productive thing to do. Only after you've exhausted the low cost options should you move to technology selection. Map your peaks. How high, how long, how often. If peaks are short and frequent and your demand charges are meaningful, batteries might be the right solution for you. If peaks are long or you also need emergency backup, generators or combined heat and power come into play. Hybrid solar plus storage can be attractive where solar is already in the picture or heavily incentivized. From there, build a clear financial model. Load in capital expenditure for each option, plus operating costs like fuel, maintenance, software, and eventual battery replacement. Model demand charge savings based on realistic peak shaving volumes, not simply the best case scenario. Add any demand response revenue based on what programs in your area actually pay. For example, $50 to $100 per kilowatt per year. Calculate payback, ROI, and net present value over a 10 to 15-year horizon and test conservative scenarios. Consider financing solutions like leases, PPAs, or energy as a service if you want to preserve your capital. Pilot and phase where needed. Start with one building, one process, or one system. Learn what actually happens to your demand line, your operations, and your bill, and then scale what works. And then, once the solution is in, keep monitoring it. Confirm savings on the bill every single month. Adjust set points and dispatch rules as your operation changes, and stay on top of tariff updates so your strategy stays aligned with the most important thing: the rules of your rate. So let me bring this back to your role. Obviously, I don't run your plant, right? That's your job. But my job is to translate all of the mess and complexity around utility billing and all of the different options that operators like yourself feel inundated by. And I want to organize those things and give you questions and perhaps arm you with leverage that you're definitely not getting from utility customer service or a vendor or the rate book. So the bottom line today on C&I Peak Shaving is this: the most cost-effective strategy for your facility is the one that takes your actual demand charge rate, your real load profile, and your operational constraints, and uses the simplest mix of operational changes, on-site generation, and storage to pull down your worst kW intervals while still keeping your core operation intact and paying back its capital inside the target window. Fair. If you want to take this further with your team, here are a few questions you can use in your next morning huddle. First, over the last year, what was our highest recorded demand in kW? What did we pay per kilowatt on that line? And during which hours and seasons did those intervals actually occur? And were they consistent with the last year or two? Second, if we look at our average demand divided by our peak, what is our load factor? And what does that say about how tall our peaks are compared to our everyday energy consumption? Third, which specific loads in our facility, HVAC, processes, pumps, lighting, or something else, are most responsible for those peaks, and which of those could we realistically reschedule or control without hurting output, comfort, safety, quality? Fourth, before we let any vendor size a battery or a generator for us, what payback period and return on investment do we need to see? And what demand charge and demand response assumptions are we willing to sign our name to in a simple model? Hey, if today's episode raised more questions than answers and you want help evaluating a high stakes energy decision like this, we built something to help you do just that. For Indiana commercial and industrial operators with a serious electric bill who are actively considering a high cost, high stakes energy decision over the next 6 to 12 months, we offer an energy decision blueprint. This is for operators who actually want to see their own numbers clearly, not people who are just curious about the topic. It starts with a short discovery call to make sure your level of energy spend, project size, margin for error, and potential savings are significant enough to justify deeper examination. It's a practical conversation all about getting to the heart of what you're considering and what your actual needs are. If it makes sense to move forward, the next step is a structured data collection process. We gather the last 12 months of bills, interval data when it's available, and sometimes we have to order it from the utility. And we get a clear picture of your shifts, major loads, and the operational requirements and restraints you have to contend with in your facility each and every day. Then we hold a 45 to 60-minute working session where I, and when it makes sense, one of our other energy engineers run all of that data through a comprehensive analysis, the same kind we use with our own customers. We look at exactly how you're currently being billed, and most importantly, why. How the project or projects you're considering would behave on your specific rate and on any other rates that might be available to you, and what the best and worst case scenarios look like in terms of cost reduction, both in units and unit cost. How many kilowatt hours and what's the cost per kilowatt hour? You have to take both of those factors into consideration. And we look at any power quality considerations you need to keep in mind as you evaluate this project. After that, you get a simple board ready 1 or 2 page summary that lays out your current situation, the realistic range of outcomes for the main options, and my view on whether there's a strong savings opportunity available to you or not. For qualified accounts, this energy decision blueprint is free, and there are only 2 acceptable outcomes. If there's a real opportunity, we'll show you exactly the next questions to ask and the steps to take for a successful implementation. But look, if there's not, we're going to get to the bottom of it as quickly as possible and tell you exactly why you should not pursue the project. And that's so you can stop wasting time on a project that really will not serve your needs. And if we uncover additional opportunities for you that you have not yet considered, we'll spell those out clearly for you as well. So if you'd like to go through the energy decision blueprint process, go to tacticalenergygroup.com and look for Energy Decision Blueprint, or you can use the link in the description below. Again, that's tacticalenergygroup.com. Thank you for listening to Energy Answers by Tactical Energy Group. If this helped, send it to another operator you know who's dealing with the same energy-related questions and headaches, and visit tacticalenergygroup.com to get more wildly practical tools for your facilities.